Our final topic when it comes to patterns of growth is how to solve exponential growth problems when we're looking for time. And so for this, it gets a little bit trickier. We have to use something called the logarithm. We're going to talk a little bit about those and how we use them to kind of undo an exponent. Okay, so let me explain kind of what we're talking about, what kind of problem. So say a town has 1,000 people and grows by 20% each year. How long until we hit, say, 2,000? Okay? And so again, if this were linear growth, this would be really simple, right? Because 20% of 1,000, 200 people, it would be 5 years, right? But it's actually going to be faster than that because exponential growth is faster than linear growth. It's going to be a lot less than 5 years. And so what we need to do is we need to think about setting this up as an exponential growth equation. So what's our equation? If we write down our explicit equation, P sub n equals our initial value, 1,000 times 1 plus our percentage, 0.2 to the n. And really, if you think back to how we solved these problems when we were looking at linear growth, we want to know, when does the population, for what n does the population equal 2,000? So 2,000 equals 1,000 times 1 plus 0.2 to the n. So we're looking for when that P sub n is equal to 2,000. Okay? And so to solve this, at first it seems pretty easy, right? You say, oh, okay, well, let's divide by 1,000, right? Divide both sides by 1,000, we get 2 equals, I'm going to write 1 plus 0.2 as 1.2 to the n. And this is where it gets tricky, right? Because you're actually asking yourself, what power n gives me 1.2 raised to that power gives me 2, okay? And so this is where we're going to use logarithms. So some of you may have seen these before. If you've looked at the notes, you've kind of read a little bit about them. But what the logarithm is what it does is it undoes exponentiation, okay? And so specifically, what happens is if you take the logarithm, so we write it log log of x raised to the y, so anything raised to a power, that's going to be equal to y times log of x. So it turns exponentiation into multiplication, which is actually something we can deal with, okay? So what we're going to do here is we're going to take the logarithm of both sides of the problem. So log of 2 equals log of 1.2 to the n. And now, because of this property, this n comes down to the front. And we get log of 2 equals n times log of 1.2. Right? So that power comes down and becomes multiplication. And this is easy to solve, right? To get this, you just take n, divide by log of 1.2. So n equals log of 2 divided by log of 1.2. So we just divide both sides by log of 1.2, which is just a number. We don't know what it is yet. We'll put it in our calculator in a minute. But if we do this, log of 2, let's see, log of 2, which is 0.693, divided by log of 1.2, gives us 3.802. So 3.8, let's say 3.8. We can round because we're at the end of our problem. So what this is saying is that in 3.8 years, the population will hit 2,000, okay? And so you can test that out. So you can always check your answers here. If we plug in 3.8 here, so if we take n equals 3.8, and plug it into our original equation. So P sub 3.8 is 1,000 times 1.2 to the 3.8. Well, what's that equal to? 1,000 times 1.2 to the 3.8 gives us 1999.35. Okay? So notice, because I left off that 3.802, which didn't seem like that much, I did end up a little bit off. This is pretty close. Okay? So in practice on these problems, for example, like on the exam, you'll have a little bit of room, but make sure you don't make any big rounding errors. Okay? So you need to be careful. So here, 1999.35, probably close enough. If you had rounded this to 4, you'd been in a world of trouble. Okay? So we'll use logarithms like this. We're not going to use them in any other way. We really just need them when we're trying to get that power n by itself. Okay? So I can give you another example. So let's look at one. We haven't talked anything about exponential decay where it's decreasing. So let's say the amount of money in an account is decreasing by 6% each year. If it starts at $10,000, when will it hit, say, $9,000? Okay? So this is another exponential growth problem, right? Because we're growing by a fixed percentage. And so if you think about your equation, P sub n equals 10,000 times 1 plus, how much is this growing by? Well, 6% is how much it's decreasing by. That's going to be a negative 0.06, okay? Because it's going down rather than up. So we're going to get 1 minus 0.06 to the n power, okay? So anytime you've got a percentage decreasing, that's going to subtract that rate instead of adding it, right? And so we get P sub n, if we combine these, 10,000 times 1 minus 0.06 is 0.94 to the n. And now our question is asking, when will it hit $9,000? We plug 9,000 in for P sub n, and we want to figure out what n is. So 9,000 equals 10,000 times 0.94 to the n. We divide by 10,000 on each side. So that's 0.9 equals 0.94 to the n. We take the logarithm of each side. Log of 0.9 equals log of 0.94 to the n. And then, just like it did before, our n comes down to the front of the logarithm. It becomes multiplication. So log of 0.9 equals n times log of 0.94. And we get n equals log of 0.9 divided by log of 0.94. And you can solve that with your calculator. Log of 0.9 divided by log of 0.94 gets us 1.70. Yep, 1.7028, let's say. So after 1.7 years, you would be down to $9,000 in your account, which, if you think about it, Does that make sense? That doesn't seem right to me. I guess it is. Yeah. So let me check my numbers real quick. Log of 0.9 divided by log of 0.94. Yeah, I guess that's right. Okay, so 1.70. Again, like I said, we can always plug it in here. We can say, what's 10,000 times 0.94 to the 1.7? And we get 9,001 and 55 cents. So it is right, even though it seemed a little low for me for some reason. Okay? So after 1.7 years, we would have $9,000 left in the account. Okay? So that's how you can solve these problems using logarithms with an exponential problem.